Now let's look at example 2 of base thickness design. We are required to design the base thickness for the pavement with the following given conditions. The characteristic 28-day flexural strength of the concrete is 4.5 megapascal. The desired project reliability is 95%. The subgrade design CBR is 5%. The design traffic for 40 years design life is 4 times 10 to the power of 7 HVAG. We have the traffic load distribution data as well. Step 1 is to select a rigid pavement type. So it's either PCP, JRCP, CRCP, or SFCP. For this example, we selected PCP, the plain concrete pavement. Step 2 is to decide whether concrete shoulders, either tied or integrally cast, is to be provided. A concrete shoulder is considered in this case. Step 3 is to determine the type and thickness of the subbase. As the design traffic is 4 times 10 to the power of 7 HVAG, so that's greater than the last category, the value in the last category. So from table 9.1, 150 millimeter lean concrete subbase LCS is selected. Step 4 is to determine the effective subgrade strength. From figure 9.1, for 150 millimeter LCS and subgrade design CBR of 5%. So that's 5%, that's 150 LCS. So we found the effective subgrade design CBR equal to 75%. Step 5 is to select the concrete 28-day characteristic flexural strength FCR, which is given in the question as 4.5 megapascal. This also meets the requirement of minimum characteristic design concrete flexural strength. Step 6 is to select the desired project reliability and load safety factor as SF. As the project reliability is given as 95%, and we chose PCP. From table 9.2, we found a load safety factor as SF of 1.3 for the rigid pavement design. Step 7 is to select a trial base thickness from table 9.7. So the minimum thickness for PCP and design traffic of 4 times 10 to the power of 7 HVAG is 200 millimeter. We have another way to determine the base thickness. So figure 9.2 is the design chart for concrete base thickness. The chart allows designers to compare and design base thickness for different traffic volumes, effective subgrade strength, and safety factors. According to the NDT of 4 times 10 to the power of 7 and previous results, effective subgrade design CBR of 75% and LSF of 1.3. This figure suggests a base thickness of approximately 210 millimeter, which is greater than 200 millimeter, the minimum thickness. So this value is adopted as a trial base thickness. The step 8 is to calculate the expected load repetitions. The NDT is 4 times 10 to the power of 7 HVAG. The traffic load distribution for SAST is shown in this table. So for each actual load, we could calculate the expected load repetitions for SAST group by multiplying the proportion of load by proportion of actual group by the design traffic. So the expected load repetitions are shown in the last column of this table. Next is step 9, which is to use equation 26 and 27 to calculate the allowable load repetitions in fatigue distress mode and F for the SAST actual group. The SR could be calculated using the below formula here, where the SE is the equivalent concrete stress in megapascal. So we will provide a bit more details in the next slide. The FCR is the design characteristic fluxual strength of concrete at 28 days. The capital P is the actual group load. LSF is the load safety factor. F1 is the load adjustment for fatigue according to actual group. It has a different value for different type of actual group. So for SAST, we just use the value of 9, and for QADT, we use the value of 72. This is the formula for SE. We are the A, B, C, D to J coefficients in table 9.4. The D is the concrete base thickness in millimeter, and EF is the effective subgrade design CBR in percent. So for this SAST case, we refer to the value for A to J in table 9.4 from the next slide. So we can just get the corresponding constant for the value from A to J. And EF is, the D, that's 210 millimeter, and EF, that's 75%. So we're able to just get the equivalent concrete stress SE as 0.751 megapascal. So this is the table 9.4. It contains the coefficients for calculating equivalent stress, equivalent concrete stress SE, both for with concrete shoulders and without concrete shoulders case. Because in the beginning, we determined to use the concrete shoulders. So we just pick up the values in the right hand side of this table, and for the SAST group. Step 10 is to calculate the ratio of the expected repetitions to the allowable fatigue repetitions and multiply 100 to obtain the fatigue damage. Step 11 is to calculate the allowable repetitions for erosion stress distress mode and E using the formula 29. In this formula, the physical meaning of P and LSF are same as before. F2 is the adjustment for slab edge effects for value of with value of 0.06 for base and no concrete shoulder case, and 0.94 for base with concrete shoulder case. F3 is the erosion factor, which could also be calculated from equation 28. F4 is the adjustment for erosion due to different type of actual group ranging from SAST to QADT. The formula for erosion factor, F3, is shown here, where the parameters A, B, C, D to J are coefficient in table 9.5 to 9.6. Again, the D is the concrete base thickness in millimeter, and EF is the effective subgrade design CBR in percentage. Equation 28 is used to calculate both SE and F3, which means The expressions are the same and only the coefficients are different. This table 9.5 contains the coefficients for calculating erosion factor F3 for angled bases, both for without concrete shoulders and with concrete shoulder cases. This table 9.6 lists the coefficients for calculating erosion factor F3 for DOT or CRCP base, again for categories of without and with concrete shoulders. If we divide the expected repetitions by the allowable erosion repetitions, NE, and multiply 100, we get the erosion damage in percentage. Step 13 is to repeat steps 9 to 12 for each load on this axial group. Next step is to calculate and sum the fatigue and erosion damages for each axial group. Step 15 is to repeat steps 9 to 14 for each axial group ranging from SADT to QADT. This table is the summary of the calculations for the axial group SASD. The first column is the actual group load P. The second column is the design load, which is P times LSF. The third column is expected load repetitions from step 8. The fourth column is the allowable repetition for fatigue distress, and the values comes from equation 26 or 27. The fifth column is the fatigue damage, which is calculated as the expected repetitions divided by the allowable repetitions and times 100. If we sum all the fatigue damage, we get the value of 124.69%. The sixth column is allowable repetitions for erosion distress, and the values come from erosion equation 29. Similarly, we could work out the erosion damage in the last column. The sum is around 6. The total percentage of fatigue damage and erosion damage are 124.69 and 5.98% for all relevant load in this axial group SASD. The previous slide is to run steps 9 to 14 to get the total damage for axial group SASD. This slide is to repeat steps 9 to 14 for TASD. The percentage of total fatigue and erosion damage are summed as 0.19% and 46.42% for this TASD axial group. Next is to run steps 9 to 14 for single axial dual tears SADT. The total percentage of fatigue and erosion damage are summed as 0.46% and 34.39% for axial group SADT. Similarly, for the data for axial group DADT is shown in this table, and the total percentage of fatigue and erosion damage are summed as 0% and 32.07%. The data for triaxial with dual tears TRDT is shown in this table. The total percentage of fatigue and erosion damage are 0 and 0.52% respectively. Finally, the data for QADT is shown in this table, and we can work out the total percentage of fatigue and erosion damage for this axial group accordingly. The total percentage of fatigue and erosion for all axial group types and group loadings are obtained after we sum all the corresponding values. So the total percentage of fatigue damage is 125%, and total percentage of erosion damage is 119%. From step 16, we can see that both fatigue and erosion damage were greater than 100%. So the trial design is deemed unacceptable. We have to increase the base thickness and to repeat steps 9 to 16 until both the total percentage of fatigue and erosion are less than 100%. Next, we slightly increase the trial base thickness as 215 millimeter and redo the calculation. The corresponding total percentage of fatigue damage is 66%, and the total percentage of erosion damage is 93%. Both percentages are less than 100%, so this base thickness is acceptable. Step 18 is to check the minimum base thickness requirements. The design base thickness is the maximum value of the calculated base thickness and the minimum base thickness from table 9.7. So based on previous calculation, the minimum acceptable base thickness for this rigid pavement design is 250 millimeter. The minimum base thickness from table 9.7 is 200 millimeter. So the maximum of both values is 215 millimeter, which is the final base thickness. Sometimes we need to consider to add additional thickness to the design base thickness to account for the following factors. If there are any limitations of paving equipment and marine systems, or future surface retexturing treatment such as diamond grading and or grooving may lead to possible losses of the base thickness, or if the pavement has an asphalt surfacing, the base thickness may decrease due to future milling of the asphalt. Step 19 is the final conclusion. The final base thickness for construction is the sum of the design base thickness and any additional thickness for the project.